So now let's see how it works a little bit and see it working with a little more detail than the original cranking. On your right you see the control section. There's a series of irregular shaped discs. They're cams. And as Ray cranks that thing, these cams rotate around. And these little wheels follow the irregularities. And they move back and forth. And they drive these rods going into the calculating section and control all the timing of all the events in the calculating section. This is what we would call today the microprogram. It's not reprogrammable. All it can do is control these events. So in this section, we do the calculating. In the method of finite differences, we can do up to a 7th order polynomial. That means an equation like this. An equation like this can be used. We just picked an arbitrary one, but you can find the right one, remember, for every function in the book. And this one is, because there's an exponent of 7, it says 8 times x to the 7th. This is a 7th order polynomial. That's the largest exponent in the equation. And you can solve it for various values of x, but it's kind of tedious. 8 times x to the 7th plus 2 times x to the 6th plus 9 times x to the 5th, etc. And you wouldn't want to do that thousands of times manually to make this book, even if you could do the method of finite differences with addition only. We'll show you that on the blackboard in a minute, or a few minutes. Anyway, a polynomial like this has to be set up into the machine. And the way we do that, I'll show you on the board in a minute, is we calculate differences with the addition. We have to manually do the additions for a number of cycles, and then we can set up the machine with those differences. And after that, all it has to do is add. So it adds from the rightmost column, which is difference column 7, since this is a 7th order polynomial capability, to the 6, to the 5, to the 4, etc., down to the 1. And it adds whatever in the 1 to the last result, and we get a new result every 8 seconds. As part of the cycle, that result is transferred by these gears and these rack and pinion things into this set of wheels that have type fonts on them. It sets up the answer that was in this column into the type fonts. The type fonts print on the paper. We don't have ink in the printer because it's hard to clean up every day. But most importantly, there's another set of type fonts that presses down into this tray. And in the tray would normally be a soft material like plaster of Paris. We didn't put that in there for the same reason, but you can see an example of it in the display case over there. And it presses the answer into that plaster of Paris, and then it indexes the tray in to go down to the next line for the next answer. So that's what's going on in the machine. I'm going to ask Ray to crank it, and you can watch the cams going around, and the cam followers driving these rods, and the rods will drive the addition process in the calculating section. Now that process means that whatever's in this register, there's a 31 digit register here. Whatever's in there gets added to this one, and the way it gets added is it counts itself down to 0 for every digit in there. And as it's counting down, it's rotating toward 0, and it turns these gears, which add the same amount, into these wheels. But now this is a 0. So it gets out of the way of the gears, it goes up in the air, and another set of gears brings it back to where it used to be.
Called the restore.
That's called restoring, in modern computer terms. Anyway, the same thing goes on for every column adding to the next column, including the final difference 1 adding to the last result, the previous result. Now you'll notice these things go up and down in sets of 4. All the odd ones, 7, 5, 3, and 1, go up at the same time. And all the even ones go up at the same time. That's a form of what we call today pipelining, although he didn't call it that. He just figured out that it was possible to simplify the design very greatly by adding them all the odds at the same time and then add all the evens at the same time. And that's the great simplification that allowed him to go from 25,000 parts to 8,000 parts. Okay, so what you're going to see when he cranks that, as these things are going up and down, you'll also hear some loud clanking noises. That is these things that look like medieval swords moving out of the way, and at the end of every cycle, after they move these things around, we're not sure the gears are all going to end up in the same place because of mechanical variations in where they land. And so what that does is these bars come up and they slam into the gears and set them exactly where they need to be.
Those bars go from bottom to top.
Yeah, they're
All the way up
they're-
to the
The
register.
swords are complete length. And any gear that has gone too far or not far enough gets put back exactly where it needs to be. That is the secret to making this thing work, where other attempts to make difference engines failed, because there would be this gradual movement of all of the gears, and they would eventually get out of place and give you the wrong answer. But he doesn't. He gets the right answer every time, and we'll prove that. Okay, so you listen for the clanks, you watch the columns going up and down, and then you watch the printer. The printer will, at the end of each cycle, the printer will come up and ink itself, and then touch the paper to the wheels, which have been set up with the proper answer. And then the other grid fonts will come down and press into the tray, and you'll see the tray jump in one level. You'll notice at the far end here, there's a lot of gears and pulleys and things. Those are formatting things, programmable. In the book, you'll notice on any given table, there's a variable number of columns. In this case, there's 2 columns per page, but you could have up to 3 columns per page, and that's programmable over there. You'll notice also that every 5th line is a blank to make it easy to read. That's programmable over here. You can make it every 3rd line, every 10th line, whatever you want. So Babbage thought not only of making accurate numbers, but easy to read books. One interesting thing is when it gets down to the bottom of the page here, it recognizes that, and it turns this gear and moves over to the next column, pulls it back out, and starts at the top of the page. And when it gets down to the bottom of the last column, something else interesting happens. There's a little weight you see down in the tray here. We probably won't get there during this demo. That weight drops into the tray, and it pulls on this little string that's going along the bottom. It's catgut. Comes up here, goes along here, pulls on this little lever, which disengages the crank so that Ray can't create any more data until we change the tray. Wow. So Babbage didn't want you to have a chance to make an answer that didn't get printed.
Sounds like Rube Goldberg.
Well, it's Charles Babbage. And the interesting thing is, he thought this up and he wrote it down. He never built it, but the darn thing works. And I'm not sure all of Rube Goldberg's stuff did. Anyway, that's what you should be looking for. And we'll do another 5 cycles, and then we'll check the answer and see where it is. Right now, the value of X is 260. And we're going to go 5 cycles till it says 265. And see what the answer is.
And then after we do that, we'll take you around back and tell you what's going on back there.
Yeah.
So here we go with 5.
See the cam followers moving in and out. You can hear the clanks of the little sword things. You can see the sets of 4 going up and down.